Hey, so we are doing area. We just started our area unit, and today we're just talking about the area of basic shapes. So we're going to go through some formulas and examples. Before we do that, we're going to talk about the terms base and height. So the base and the height, these terms are very often used when we calculate area. They're going to show up in a lot of formulas. The most important thing to remember is that the base and the height of a shape are always perpendicular, which means they make a 90-degree angle. So all we're going to do is go through these examples right here and highlight the base of the height. I'm going to highlight them and then also label them with a B for base and an H for height. So in this first triangle, here's our 90-degree angle, red intersecting blue. That means that either one of these, it doesn't matter which, one is the base, one is the height. This segment right here isn't 90 degrees to either of the others, so that is not the base or the height. All right, the next one, where I see a 90-degree angle, so the base and the height, I gotta stick with my colors, the base and the height are two of the segments that create that 90-degree angle, so I could call this the base and this the height. Okay, next one, here's my base, and here's my height, those two parts that make a 90-degree angle. I'm gonna call this bottom my base, and this 4 right here is my height. Actually, this shape in particular is pretty unique because since these two segments are parallel, we have actually two bases. I could also highlight this top, and I could call that base number 2. This has two bases and one height. All right, and the next one here is my base. Could be any of these. And there are no segments that make a 90-degree angle with that base, so you have to draw in your own height. So I'm going to draw in a height right here, make a 90-degree angle, and I'll call that my H. All right, moving on to the formulas, we're going to talk about rectangles and squares. So rectangles and squares are special because they have 90-degree angles. So it's very easy to identify a base and a height in any of them. The area formula for a rectangle or a square is just base times height, as simple as that. We're going to do an example of this and see what it might look like. So for example, I'm going to actually draw a square, tick marks on all the sides, 90-degree angles, and I'm going to put a diagonal and say that that diagonal is 10. So since we're missing the base and the height of this, you would have to do a little bit of extra work. And I know that to solve this, I would compare to my reference triangle, 1, 1, root 2. And after doing that, you should be able to figure out that the missing sides are 5 root 2 and 5 root 2. All right, so our area is base times height. That's 5 root 2 times another 5 root 2. And that gives us 5 times 5, 25 times 2, and that's 50. I'm going to use U for units, 50 units squared. All right, moving on to triangles. There are two different types of triangles that we're going to see. One of them is just a right triangle. If you have a right triangle, that's great because that means you already know the base and the height. So in a right triangle, the base and the height are really easy to find. If you don't have a right triangle, you will have to draw in the height, and the whole thing would be the base. This would be the height. Our area formula for a triangle is 1/2 times base times height. Another way that you might see that written is area equals, instead of writing the 1/2, you could do base times height and then divide your answer by 2. Those formulas mean the same thing. All right, for our example in this one, I'm going to find the area of an equilateral triangle that has a side of, let's say, 8. So I'm going to draw my equilateral triangle. I know all the sides are 8, and that means that my angles are 60 since all the sides are 8. Now I know that the base is 8. I do not know the height. To find the height, we have to sketch the height in. You now have a 30, 60, 90 triangle, and using special right triangles, I can figure out that this is 4 radical 3. So my area is 1/2 times my base, which is 8, times my height, which is 4 radical 3. I'm going to do this in order. 1/2 of 8 is 4, times 4 is 16. I get 16 radical 3 units squared. All right, now we're going to move on to our special shapes. So the first is a parallelogram. A parallelogram is actually just a slanted rectangle. It's a rectangle that has tilted over to a side. So that the only thing that really changes is that the base is still exactly the same. The difference is that you need to draw in your own height if it's not drawn in already. So you have to draw in a segment that is 90 degrees, and we'll call that H. And once you do that, the area is exactly the same. The base times the height. The entire base times the height. All right, so an example of a parallelogram, we'll go over here. So we'll draw a parallelogram, and I want you to label one of the corners of your parallelogram. I'm going to make these parallel. One of the angles, 45 degrees. I'll call this 8 and this 10. All right, so 10 is our base, right? We need to draw in our height, 90 degrees. And when you do that, you create a right triangle right here. And again, using special rights, these come up a lot. If the hypotenuse is 8, I know that my height would be 4 radical 2. You can sketch the reference triangle if you need it, but I've had a lot of practice. I know that this is 4 radical 2. So my area is the base of 10 times 4 radical 2, which is 40 radical 2, and that's u squared, units squared. All right, we have about 3 shapes left. The first is a rhombus. The plural of the word rhombus is rhombi. Looks pretty weird. So a rhombus is just exactly the same as a parallelogram. It has a base, and then you can also draw in the height like that. So you could say that the area of a rhombus is base times height. There are 2 ways to calculate the area of a rhombus. The second way is if you take the same exact rhombus, I'm going to draw it right here. We can draw 2 different diagonals. I'll call this diagonal 1, D1, diagonal 2. You could say that the area of a rhombus is 1/2 times diagonal 1 times diagonal 2. And both of these formulas work exactly the same. It is up to you which one you use. It usually depends on what information is given in the original problem. So the rhombus that I'm going to calculate over here, the example I'm going to give you, sketch a rhombus, put tick marks on all the sides, and we are going to draw in both diagonals. I'm going to give one of these sides the label of 13, and one of them I will call 5. All right, so in this case 13 can be copied all the way around because of those tick marks. And so I know 13 is the base, but it doesn't look like I know what the height is. I'm going to instead focus on this diagonal. I know that a rhombus has diagonals that are bisected, so I can call that 5 and 5. I also see here a 5, a 13, and I can figure out this side right here using a triple, 5, 12, 13. So this would be 12, and if that's 12, this is 12. So my diagonal 1 is, I'm going to write diagonal 1 is 12 plus 12, that's 24. Diagonal 2 is 5 plus 5, that's 10. So the area is 1/2 times 24 times 10. 1/2 of 24 is 12, times 10 is 120 units squared. All right, the next shape should be pretty familiar. It's a trapezoid. Trapezoids, their defining feature is that they have one set of parallel sides. Since they have these parallel sides, it actually means that they have 2 bases. So I'm going to write here that they have 2 bases, and we usually call those base 1, and base 2. So the 2 bases, if you connect them perpendicularly, right angle, this is your height. And you can draw this height anywhere. It can be here or here or here, but it's helpful to put it on one of these corners because then you make a right triangle. All right, the area formula for a trapezoid is 1/2, in parentheses, you add the bases, base 1 plus base 2, multiply by height. You could also write this formula like this. Area equals, in parentheses, base 1 plus base 2 times the height, divide that by 2. Okay, we're going to do a pretty simple example for a trapezoid. I'm going to draw like a different looking trapezoid here with parallel sides. I'm going to make this a right angle. We'll say, what if this is 10 and this is 18 and this height is 5? So in this case, I actually have all the information I need. I have both bases and I have the height that connects them. So if you wanted to, you could draw this height here as well, and that would be 5. All right, so our area formula is 1/2. I add the bases, 10 plus 18, and I multiply that answer by 5. So I'm going to do this in parts. I'm going to do 1/2. I'm going to add 10 plus 18 and get 28. Multiply that by 5. So 1/2 of 28 is 14 times 5, and 14 times 5 is what, 70? Yep, units squared. All right, we have one more example, and it's a kite. So the defining characteristic of a kite is that the sides next to each other, the adjacent sides, are congruent. Another special characteristic is that if you draw the diagonals, they intersect at 90-degree angles. So we have these right triangles that are formed. We're going to call the diagonals diagonal 1, and this one would be diagonal 2. And one more thing you might want to notice about a kite is that this shorter diagonal always is bisected. All right, so the area formula for a kite is 1/2 times diagonal 1 times diagonal 2. It's the same as a rhombus, and that's because a rhombus can be considered a kite. All right, the other way you could write this means the same thing as diagonal 1 times diagonal 2 divided by 2. All right, the example kite that I'm going to draw over here, I'll sketch in my kite with two congruent sides, and I'm going to give this side as 10. I'm going to draw one of the diagonals, say this is 8, and this up here is 2. So my formula is 1/2 times diagonal 1 times diagonal 2. I actually have one of my diagonals. Diagonal 1, we could say, is this entire length, 8 plus 2. So I know that's 10. So I'm going to start filling this in. So I could say this is 1/2 times 10. Now we just need to figure out diagonal 2. So diagonal 2 is this length. I don't know it, but I do know that a kite makes right angles here. And this right triangle, I think, is in a triple family. If I take the Pythagorean triple 3, 4, 5 and multiply it by 2, I get 6, 8, 10. So I think that this missing side is 6. In a kite, we know that this shorter diagonal is bisected, so this is also 6, which means that this diagonal together is 12. So I'm going to say this is 10 times 12. That means that our area is 1/2 times 120, which is 60 units squared.